Welcome to another coding tutorial, and in today's video we're going to be making this Hilbert curve using recursion. So what is the Hilbert curve? The Hilbert curve is a type of a space-filling curve, which is a curve that passes through every point in a 2D or 3D space without ever intersecting itself. It is named after David Hilbert, who first described it in 1891, and it has a shape that looks like a cup. We used recursion to construct the Hilbert curve, with each level of recursion representing the higher order. So if you look at this picture, when the order is equals to 1, there's only one grid that is filled with one cup. And this cup is made out of 3 joints. But when the order is greater than 1, let's say in this case it equals to 2, the grid is subdivided into 4 quadrants, each occupied by a cup that is joined by 3 joints. And as the order increases, the smaller grids are also subdivided into 4 smaller quadrants, each with 4 cups and joined by 3 joints. And if you look closely in each of the 4 quadrants, the configurations are not the same. The configurations of the first 2 quadrants are actually unchanged, while the third is rotated 90 degrees and the fourth is rotated -90 degrees. And this is both for the smaller grid as well as the big grid, as you can see here. Since we'll be using recursion to construct the Hilbert curve, let's review the 3 main properties of a recursive algorithm. First, it needs to call on itself. Second, it needs to have a base condition at which, once reached, we exit out of this recursive function. And third, it needs to work towards this base condition so that we ensure that we exit out of this recursive function eventually. Let's start by figuring out the base condition, which is when the order equals to 1 and we only have one cup that is made out of 3 joints. So I'm going to start by actually declaring size. And I'm going to set size to 400 and replace the width and the height here with the variable size. Then I want to move the origin point from the top left corner here to the middle of the canvas. So what we can do is that we can use a translate function and translate it to size divided by 2 and then size divided by 2. Now before we start drawing the joints, I want to start by drawing 4 points so that you can see where are the 4 points that will connect to make up the 3 lines. These 4 points, if we were to divide this square into 4 smaller squares, they're the center of each of these squares. So they're going to be at the location of negative size divided by 4, negative size divided by 4. Let's make it a size of 10 by 10. Right now, everything that is to the left of the origin point will be negative, and everything that is above the origin point will be negative, right? And that's why this one is negative, comma, negative. The second point will be negative size divided by 4, and then size divided by 4, 10, comma, 10. Then we'll have this bottom left here. Then the third one will be size divided by 4, and then size divided by 4, 10, comma, 10. Then we have this one here, and then the last one will be size divided by 4 and negative size divided by 4, 10, comma, 10. Alright, so now you can see that these are the 4 points where we will be connecting the line, right? So now let's use the line function, which takes in a total of 4 arguments, the 2 x and y coordinates that will connect together to make a line. So we actually already have all of these points. So let's do the first line, which will go from this point here to this point here, and it will be negative size divided by 4, negative size divided by 4, and size divided by 4, and negative size divided by 4. All right. And then the second line will be from negative size divided by 4 and size divided by 4, negative size divided by 4, and size divided by 4. No, this one has to be negative. All right. And then the third one will be line of size divided by 4, negative size divided by 4, size divided by 4, and size divided by 4. Great, so now we don't actually need any of this. So that is when the order is equals to 1. Now, how about we start by writing our recursive function with this base condition. So I'm going to create a function. Let's call it Hilbert Curve. And we're just gonna copy and paste this set of code in here, and then we can just call Hilbert Curve. So now, because it's going to be a recursive function, we need to provide some parameters here. The first one I'm going to provide, the first two are going to be cx and cy, which is going to be where I want to translate it to, right? Which is the center of the cup. So let's do that. And then how about we also provide the size in here and order, right? So cx and cy for this first one will be size divided by 2 and size divided by 2, and then size will be 400, right? And then order is 1. Let's just put order here, and then let's declare a variable called order, set it equals to 1. Let's click run. Okay, it works. Now the next order, which is when order equals to 2, what we want to do is that we want to subdivide this square into 4 smaller squares, right? 4 smaller grids. And then we want to have 4 cups filled up these spaces and then joined by 3 joints. Inside here, we want to create a base condition, which is if order is greater than 1, then we will be calling the Hilbert curve again. And we'll be calling it where? So what are the cx and cy for this? So how about we start with just the first one, which is when cx and cy will be at negative size divided by 4 and negative size divided by 4. And then the size will be what? It will be half, right? Because we're going to be subdivided here. So it will be size divided by 2. And then for order, what do we want to put in here? We want to put in order minus 1, right? Because we want to work towards the base condition such that eventually the order will be equals to 1, and then we'll exit out of this condition here. Let's click run. Nothing happens because now order is equals to 1. Let's click 2. Okay, so 2 things that we need to fix. The first one is that, as you can see here, this bigger cup is also moved to the left here, and that is because when we use a transformation function, we need to consider whether we want to use the 2 additional functions, push and pop, or not. And push basically saves the transformation that we use, and then pop returns it back to the original settings before the next one is called. And that is what we want to do, because we want to translate everything based on the original point where x and y equals to 200, 200. So we will put push before translate here, and then pop here. All right, so now we have 2 cups, but it seems like the smaller cup is done correctly in terms of the location and the size. But this first cup, it seems like these line functions are not done correctly. So if you look at this picture here, the location corresponds to the recursive order, specifically by size divided by 2 to the power of order plus 1. So in the case where the 2D space has a size of 100, when the order is 1, we only have 4 coordinates that connect to make up the 3 lines. But when the order is 2, there are more than just 4 coordinates now. The locations still correspond to recursive order, which is size divided by 2 to the power of 3, or size divided by 8. We can still draw the first line, the top line, the same way, while the left and the right lines are now at a distance that is size divided by 8 from the left and from the right border. So let's declare that variable that corresponds to the order, specifically 2 to the order plus 1, right? So we're going to declare that variable. Let's call it n. And I'm going to use a function called pal that takes in a total of 2 arguments. The first one is the base, so our base is 2. And the second one is the power that we want to raise the base by. So it's going to be order plus 1. Then, for the top line, actually, if we replace this value by n, it should already fixes itself, which it did here. But if I were to do it to the second line, which is the left line, as you can see here, it moved everything to here. The size is correct, but we actually want it to be at this point here, right? And the reason that it is here is because relative to the origin point here, it's moved to the left by size divided by n, right? But we want to actually move it by that amount from the left border. And we can just subtract size divided by n here from size divided by 2, which is the distance from the left side of the origin point. So what we can do is we can do size divided by 2 minus size divided by n. And because everything is relative to the origin point here, we need to also put a negative sign here for the left line. And we just copy this one and replace this with the third argument here. All right, and then for the right line, we just use the same logic, but instead of this negative number, we just do it with a positive number. And this will be n. This will be n. All right, now we only have 1 cup here, so we want to add 3 more cups. So let's work with this cup first. So the location of Cx and Cy will be size divided by 4, right? This point, and then negative size divided by 4. Let's click run. All right, and then how about the third cup, which is at negative size divided by 4, and then size divided by 4. That doesn't look correct. And before I fix this, let's just add the fourth cup. So at size divided by 4 and size divided by 4. Okay, so how we want to fix this is that we want to rotate this third quadrant here 90 degrees, right? And we want to rotate this cup by negative 90 degrees. So how about we add another parameter and let's call it angle. And what we're going to do is that we're going to rotate the cup by the angle provided as an argument. When the order is 1, that angle will be 0. Then this is the top cup here. We don't want to rotate it. The second cup, no rotation. The third cup here, we want to rotate clockwise, so 90 degrees. And then the fourth cup here, we want to rotate counterclockwise, so negative 90. And because we're using degrees for all of these, we also need to set the angle mode to degrees. Ta-da! All right. Okay, now how about we increase the order to 3. As you can see here, this shape here inside this top left quadrant is the shape that we saw as when order is equals to 2. And you can see that this grid here is rotated 90 degrees to the right. This one is rotated 90 degrees to the left. So both the smaller and the bigger grid is rotated based on the angle that we provide here. And now we can just increase the order. And how about if I increase it to 10? And it's completely black. And that is because the Hilbert curve is a space-filling curve. So as you increase the order, it's supposed to just fill up the whole space. And now it's just completely black. This might actually crash your program. And that is because I drew everything in the draw loop and the order is really high. So you can actually use the function called no loop, or just put everything inside the setup function so that it's only called once. How about we decrease this down to 7? That looks cool too. So I hope that you enjoy this one. This is one of the popular applications of a recursive function, and I think it makes a very interesting pattern. So give this one a try.